Okay, good afternoon. So yesterday we left at at a point where we were discussing how in a pneumatic system a capacitance can be realized, a capacitor and a resistor, and we said that this orifice here um, can be treated as a resistor, and delta P, the pressure difference across the orifice, can be treated as the voltage, the potential difference across this point and this point, and Q is the flow rate. So one thing I will let you guys know that for this topic of pneumatic systems that we are discussing, of course you can refer Bentley, and also there is another book by Ogata. So I have taken mostly from the material is prepared mostly from Bentley and Ogata, and for more detailed discussions you can definitely refer these two. So please take a note of that. So what we said is yesterday, we looked at how the capacitance is going to look like in terms of the volume of the vessel here and the change in density del rho del P, right? And then if we actually started looking at this, that's we said that since capacitance equals the change in gas stored, the mass in change in the mass of the gas stored, a change in the gas pressure, right? This can be equated, so del M by del P can be, and so this is one portion, and then we also had C multiplied by del, so the change in the pressure multiplied by the capacitance equals the flow rate multiplied by the time, so which will give del M, right? So so this guy is nothing but this guy, right? So del M, so this is del M, Q into del T, so dm is equal to Q into del T, right? The flow rate multiplied by the time is the del is equal to the incremental change in mass, right? And divided by del P is the capacitance, right? So then now Q, what is Q? So we have to replace this Q and dt. So dt of course comes here. We have to find Q, and Q, as we can see from here, this equation. If you look at what is Q, so Q is equals, so the flow rate equals the pressure difference across these 2 points divided by the resistance offered by this orifice, right? So then I can write C multiplied by dp0 dt. dp0 is this, the small incremental change in the small signal pressure, equals pi minus p0 divided by the resistance, right? And then if I take if I take simple Laplace of this, I can represent the output pressure P0 divided by Pi equals 1 by RCS. So this represents the normal, so a simple RC kind of a circuit, right? If you see the output pressure, so if this is V0, this is Vi, so V0 by Vi is given by 1 divided by 1 plus RCS, right? So this system represents something very similar. Okay. Now let's proceed to the flapper nozzle amplifier, which again is a very important amplifier used in pneumatic systems, and let's look at this in detail. So the power source for this amplifier is supply of the power source for this amplifier is supply of air at constant pressure PS. So we have constant pressure PS being applied at the orifice, right? And a small change in the position of the flapper X, the small change. So what we have here, we have air supply coming here, and this goes to a control valve, and we will discuss this a little later in the next slide, how the feedback is realized, but we have an air supply pressure being given as PS. There is an orifice, and then we have a back pressure PB created by, so this is a flapper. Flapper means this guy can move around this equilibrium position. So here there is a pivot. This guy cannot move, but this can move. This can move like this, right? And by virtue of this movement, we can control the gap between the nozzle and the flapper, and the gap is denoted by X, right? So, so here we are going to talk of pressure in terms of the gauge pressure. So when we talk of gauge pressure, it is relative to the atmospheric pressure. So the atmospheric pressure, we assume the atmospheric pressure to be zero psig. So please understand the difference between psi and psig. You can do a quick Google search to understand to figure out what is psi and what is psig. And here are the dimensions. We have an orifice diameter of 0.25. So this guy has a diameter of 0.25 millimeter, and then there is a nozzle of diameter 0.4 millimeter, right? So what is the maximum back pressure that this guy can experience? So this will be equal to the supply pressure. And when will this condition happen? When X is zero, meaning this flapper completely touches, the flapper completely moves and closes the nozzle, right? If the nozzle is completely closed, then eventually PB, the back pressure, will be equal to PS, right? And what is the minimum pressure that we can have here at the back pressure at this point? This will be equal to atmospheric pressure, and that will happen when the flapper completely moves out and the atmospheric pressure. So basically this air supply, right, will not, this is just a supply, right, and we have atmospheric pressure on this side. So the back pressure will be equal to the atmospheric pressure when X is significantly more than the orifice diameter, right? So we have the orifice diameter here as at 0.25, and if this guy moves far away compared to this orifice diameter, then we can say that the back pressure, the minimum back pressure, will be equal to the atmospheric pressure, right? So now we actually look at, so if this is X, so we discussed what will be the maximum and what will be the minimum. So this is atmospheric pressure minimum, and this is atmospheric, this is the back pressure, which is going to be maximum when the flapper is closed, right? So again, please note that we are talking in PSIG. Please understand so this is a gauge pressure. So atmospheric pressure is considered to be 0 PSIG. So it's whereas a higher pressure compared to, so it's relative to the atmospheric pressure, right? So so you can see between for a pressure of the air supply between 15 to 3 PSIG, there is a linear kind of a behavior we can see. The overall behavior is non-linear, but then there is a linear kind of approximation we can do, right? And that means, and this is an open loop system, right? There is no feedback in this system, right? So now, and of course, this is like an open loop amplifier, and the amplifier converts the displacement into a pressure signal, right? A small displacement that we have here is converted into a pressure signal, which is equals to the back pressure that is seen here. And this back pressure can be actually used to control valves. And we will see now, based on this, right, we will create a little bit more involved system where there will be feedback. There will be feedback taken from PB, and it will be fed back to control the input itself. We'll look into that. But the point is, this is an open loop system, and there is inherent nonlinearity. And wherever there is inherent nonlinearity and it's an open loop system, let's see if we can build up a system with a feedback. For large power delivery, usually used to drive a pneumatic relay which works as a power amplifier. So this can be used to for large power delivery. We'll talk about this in the next slide. and how it can be used to drive a pneumatic relay, which drives a power amplifier. So this means we have another kind of. So this is like a small signal amplifier, wherein a small displacement X can create a pressure signal, which will be controlling the control valve, and the pressure signal is PB. This is the output signal, right? And this signal can be used as an input to a larger pneumatic relay, which will work as a power amplifier. So let's look at that. So so this is the nozzle flapper sensor, right? So we have a fixed restrictor here, and we have a variable restrictor. So the same thing that we discussed in the last slide, we are going to do a little bit more of maths and establish the nonlinear relationship. So we have a fixed restrictor and we have a flapper here, right? And then we have the vessel, the output pressure is P with a volume V, right? So this is a transmission tube connecting to an indicator. So what will be the electrical equivalent for this? So in the previous slide, we saw that an orifice can be treated as a resistor, and we had the vessel, right, which we approximated. We said that this can be equivalent to a capacitor, right? And here we have now a nozzle, the same flapper nozzle that we discussed in the last slide, with a variable gap, and this can be treated as a variable resistor. So this is the electrical analog for a nozzle flapper sensor. And let's quickly establish the relationship of such a sensor. So if you see, what is the mass that is entering this vessel of volume V? So we have a supply pressure PS, and there is a flapper. So we have the mass that is entering the orifice is given by, the change in mass is given by m dot O, and the change in mass in the nozzle is given by m dot N, and this is the change in the mass in the volume in this vessel of volume V. So obviously, so if we think of this like a KCL kind of an equation, right? The mass, the change in mass in the nozzle, and the change in mass, the change in mass in the orifice equals the change in mass in the nozzle plus the change in mass in the vessel, right? Which is what, if we rearrange, we can write like this, right? The mass change in the vessel is given by m0 minus mn, right? And if you look at this ideal gas equation, we can represent, so the moles of gas is equal to the mass in gram divided by the molecular weight, right? So, you know, I can rearrange this equation in this form. I can rearrange this equation in this form. Just you replace N with mass G and the molecular weight, right? And this R theta comes down. And here, because we are taking the differential of this, we can represent the change in the mass of this volume in terms of the pressure change and the pressure change in this, right? And it is easy to change, I mean, easy to measure. Why do we need this kind of an equation? Because it's easy to measure the change in the pressure, right? And then we know V is the volume, we know W also we know is the molecular weight. So let's look at, you know, these are gas constants. This equation is well known, right? From class 12 physics, this is well known. If you want, you can revisit this equation. And there is one more equation, that I have not again derived. You can refer. I think it is there in Bentley. Yeah, this is there in Bentley, wherein this expression, the derivation of this expression is shown. But easy thing to kind of understand is the change in the mass of the orifice is, so this, by the way, let me tell you the equation also, I think this is, you can refer Bentley, as I said. Let me tell you the chapter name also, from where you can get, so the chapter name is 12, refer chapter 12. For this equation, you can refer chapter 12 of Bentley. And so this is for an equation for compressible airflow. So, so if you see here, the change in mass is given by CD, the discharge coefficient, multiplied by the area of the orifice, multiplied by square root of the density and PS minus P. So the difference in pressure is across the orifice is PS, the supply pressure, and the pressure at this point. So this part of the expression you can look into Bentley chapter 12 and see how they have derived it. And by the same token, please understand what is going on here. This is not as straightforward as this orifice. Here we know the area of the orifice will be given by pi d square by 4, right? Where d is the diameter of the orifice. For the nozzle here, please look at the expression. The area of the discharge is given by the circumference of the nozzle multiplied by the distance x of the flapper away from the nozzle, right? So this is M0 and M0 dot and Mn dot. So if I replace these two guys here, in the steady state, of course, M dot will be 0, right? There will be no, in the steady state, the change in mass in the vessel will be 0. And in that condition, if I equate these two, right? And because we are dealing with pressure measured in gauge, we can assume the atmospheric pressure to be 0. So then we can equate these two equations. I mean, these two equations can be equated, and then we end up getting an expression of the pressure P, which is the pressure in this volume, as a function of x. PS is constant, we know PS. Dn, the orifice at the nozzle, we know Dn, the diameter of the nozzle, and we also know the diameter of the orifice through which we are supplying the air pressure, right? So if you see, so this is the expression that we end up getting. And so this is what, for this kind of a flapper nozzle sensor, this is the overall relationship that we, again, this is a nonlinear relationship. So we will need feedback, and which is what we are going to build a feedback system around this. So any questions up to this point? So pardon me for not deriving these equations, because then the scope becomes too large. So that is one of the challenges of this course, that if we try to look at each equation, then the course will never end. So you can, as I said, you can refer chapter 12 of Bentley and see how they have derived it. Okay. So another thing is, typically the time constant for such systems are pretty large and making it unsuitable for open loop use. And that's where we are discussing these sensors in the context of feedback, right? So let's now try to build system with feedback and see what happens to the problems of nonlinearity and time constant, or the bandwidth, right? But before we go there, before we build the feedback system, let us look at pneumatic relays, which are nothing but power amplifiers. So these are nothing but, you can assume as power amplifiers, where the input pressure, so this is, let's say, the input pressure, the back pressure that we talked about in the nozzle. That back pressure can be amplified. There is another power supply in the, you can think of a large power supply equivalent. This is actually an air supply, but you can think of a large battery, large power supply available, using which we can drive the final output signal, the control signal, which will be driving the pneumatic valve, right? So this works as a power amplifier and low time constants. So these amplifiers are pretty fast. And one thing that, so these are also, I mean, you can see that these are bleed type relays. So why these are bleed type relays? Because if you see the area, I mean the air that we have here, that constantly bleeds out of the system. Let me, yeah, so yeah, so the if you see, right, so there is a diaphragm here, sorry. So there is a diaphragm here, and the total movement of the diaphragm is very small, and in all the positions of the valve, except at the position where we can shut off the air supply completely, the air continues to bleed to the atmosphere. So if you see here, right, so let's say we want to, ensure that PC is equal to the power supply. In such a scenario, we will be shutting off this valve, will be shut off completely, so that the complete air goes here, right? However, in all other conditions, in all positions except where you need this valve to be shut off, air continues to bleed to atmosphere even after equilibrium. So whenever, so let's say PB, which is the back pressure, the signal that we are feeding back, and let's say that will be equal to some proportion times KPC, right? Let's say this is some proportion times the control signal. So that, as long as this does not need to shut off the complete airflow, there will be some air always leaking to the atmosphere, and hence this is known as a bleed type relay. There is another relay which is of non-bleed type. Of course, if you have a bleed type, the next one will be a non-bleed type. In this one, the air bleed stops when the equilibrium condition is obtained, and therefore there is no loss of pressurized air at steady state operation. However, the non-bleed type relay must have an atmospheric relief to release the control pressure PC from the pneumatic actuating valve. So let's look at how, so this I think you can understand. So when PB is kind of settled, right, when this is equivalent, so here, so these are like, you can think of these as like bellows. So these are like movable, you can, so these, using this, this is a solid piece of, you can think of separation. So this guy can move around, and this is like an air bellow. And if at the equilibrium condition, when we have the desired back pressure developed, right, which is again equal to, like, let's say the K times PC, right? When this is realized, then what happens? So this pressure, if you see here, this pressure will be equal to, this pressure will be equal to K times the PB. So this pressure will be equal to PC, and that will ensure that there is no more movement of this guy here, and then this is kind of sealed. So in that case, you can see that there is no leakage from here to here. There is no leakage, right? The leakage will be there. The leakage will be there only when it is trying to settle, and that is important, because if the leakage is not there, right, then you will not be able to. So there is a release. So this also works as a release path. In case you want to kind of release the pressure, right? What you will do is you will probably have a control of this guy. You will kind of release this, and this complete control pressure will be released to the atmosphere, right? So at the condition, there is no one second. So at the equilibrium condition, there is no air bleeding to the atmosphere. So hence, this is another kind of a relay known by a non-bleed. It's called a non-bleed relay. So Let's look at now. Now we will go into realizing proportional controllers using feedback. So let's see. So and here we will look at two kinds of proportional controllers: force distance and force balance. So here, so let's spend some time here. So this is a little bit interesting. So you can see the feedback is there in place now. So this PS is my air supply. This is the control pressure that this is the pressure that I want to control. And I have a sensor system realized by having this kind of a structure. So this control pressure is sensed here, and two things to note here. First is this is the input signal is given here, the error signal is given here, and this guy is also movable. Unlike the flapper nozzle system where only one end was movable, here because we want the feedback, both ends are movable. So we have the input signal given here. If we want to change the control pressure, we can move this guy, and that will change the control pressure based on the input signal. However, there is a feedback mechanism, and why do we need feedback? Again, because we want to make the system linear, and we want to improve the bandwidth of the system, right? So let's mark these variables. Let's mark these variables. So this gap, let's mark the operating point as X bar and the incremental value as X. Here, this movement, let's mark as Z. Z bar is the average or the operating point, and small z is the incremental movement. And then we have another variable here where this guy can move out based on the pressure that we are sensing, right? Flapper can be moved by both the input signal and the feedback signal, and that's what we need, right? We need that this guy should be able to move. We should be able to control by giving an input signal, as well as to ensure that it settles in a equilibrium position in a linear zone. We need to give the feedback of the control pressure back to the input here. So the proper operation of the controller requires that the feedback bellows move the flapper less than the movement caused by the error signal alone. So this is again very important if you think from a control point of view, right? If this is not the case, right, then the operating point that is maintained, if the feedback itself is so large, that means what, the system is going to become unstable. So essentially we need to ensure that for the system to remain stable and to operate in a linear region, we need to ensure that the feedback bellows move the flapper very little compared to the actual movement that we have done to control the air pressure here. Now let's do a little bit of maths. So let's say we move the top end of the flapper by an amount E. So we are going to use superposition principle. We will assume that this node is not moving for the time being. The feedback mechanism has not kicked in. This node is stable. This is stationary. This flapper has been moved in one direction by an amount E, and because we have the distance between, so this is A, and from the nozzle to this is B, right? So the effective movement seen here, you can do from similar triangles. This will be a fraction of E, and what will be that fraction? That fraction will be given by B divided by A plus B multiplied by E, right? So this is straightforward to understand. So this is B divided by A plus B divided by whatever. This you can think of a similar triangle and get this expression, right? Similarly, when this guy is thought to be stationary and there is movement here, then what will be the movement seen at the nozzle? So this will be given by A divided by A plus B multiplied by Y, right? Any questions? This should be straightforward. and then the overall movement will be, so this guy had tried to move the flapper closer to the nozzle, and the feedback, assuming that it's a negative feedback, and we'll see that it will be a negative feedback or not. Assuming that it's a negative feedback, this will try to move the flapper out. So the effective will be minus, right? So now let's do some simple maths, and some of it is, we'll leave it at pure algebra. So the back pressure PB is a function of this incremental change in the gap, and let's assume that this is a linear function, right? Assuming the whole thing will be actually operating in a very small operating point, and there we looked at the transfer function, right? We looked at how it would behave like. So we are, let's say, going to operate it here. So this was our x, and this was PB, if you remember, from one of the curves that we discussed, right? And so PB is equal to also, so this is for this movement, X movement is this, and this PB is also a function of Z here, because if this guy is moving, what will happen is there will be a change in the pressure here. So let's assume there is a linear relationship between this pneumatic relay, the change in the pressure caused by the movement in this pneumatic relay, and that is proportional to Z. And then we have the third element, which is going to control which this bellow here, and this movement PC is going to move. So this PC is going to change. Sorry, so we'll talk about this later. This PC is going to change based on this movement Z, right? So this will also be a function of the Z movement, but with some other constant K3. And K3 will be dependent on this. What will be K3 dependent on? Will be dependent on this orifice, this spring constant, this area, and all that, right? So if we simplify, so PC is equal to K3 into Z, and I'm replacing Z with PB here. So K3 and K2 goes here, right? And then if I work backwards from PB, I can replace this as K1X, and I end up here. So that means I end up with an expression which shows that yes, the control pressure, this is what we are controlling, is proportional to the amount of displacement we have seen here, right, at this point. But that is not our input signal, right? That is not our input signal. So we still have to derive an expression with respect to E and PC. So we're coming there. So hold on till we go there. And also there is another equation we need to deal with. So here the fact that we have now said that okay, PC is proportional to X, and of course these will be the proportionality constants. There will be three items involved. One will be, this nozzle here itself, right? The orifice diameter of the nozzle itself will have K1, K2 is a function of this guy here, and K3 is a function of this guy and this whole structure here, right? So combining all these three, we can say that PC is a function of, it's linearly proportional to, the displacement X. However, we still need to figure out what this guy is doing, right? So the area times, so let's say this is the area, times the pressure that we see here. Please note, whatever is the pressure here is at equilibrium point. This is the same pressure here, right? It's not that the pressure here is anyway different compared to this, right? Please note, whenever there is a pressure difference we are referring to, right? If this is PB, this at this point also this is PB. But right here, this is PC. Along this whole thing, it is PC, right? So the area times the pressure here, PC, is equal to the bellow constant. You can think of it as a spring constant multiplied by Y, right? So this is another thing that we need to take care, right? We have dealt with X. we have to now deal with y as well, right? So now let us see if we can represent this. Let's see. So this is going to be the final representation of the block diagram, and this is how it is going to look like. If you see, this is the error signal, that this is the input signal that we are given, right? We say that there is an error. Error means, so let's say we are actually measuring the control pressure here, and there is we know that what should be the control pressure, and based on that we say, okay, there is an error of whatever, let's say um, from the desired value, either the PC is more or less. Depending on that, we will be changing this, right? So that is the error signal. So that error signal is going to be multiplied by a constant which is given by these dimensions. This is what, so this part is this, right? And then what will be the feedback? The feedback will come from here, and that is multiplied by this. So this guy comes here, right? And what are we feeding back? Of course, the output, right, which is PC, right? So PC is being fed back with a multiplication factor of A divided by A plus B, which is dependent on the dimension here. On top of it, this guy will also come into picture, right? Because this is the force balance equation. So this comes because of the geometrical placement of the nozzle with respect to the input signal, where we are applying the input signal and where we are applying the feedback, right? However, this comes from the actual physical construction of the bellow, of the spring constant and the area and all that, right? So then, so this comes, so PC is equal to, so YS, right, is equal to A by KS. So from this, you can relate to this, right? Right? So now that we have our block diagram completed, so what will be the transfer function looking like? The final control pressure PC divided by ES. If we work out, if we do the algebra here, we will see that all these are actually constant, and this is KP, and hence the name proportional controller. Right? Any questions up to this point? So here, using feedback, what we have been able to do is realize a proportional controller. We talked of this pneumatic relay. This works as a power amplifier. This is a small signal amplifier. So what are the components that we see here? This is a power amplifier. This is a small signal amplifier based on the flapper nozzle. This is the feedback mechanism realized by bellow. So you can think of this as a resistor feedback kind of a network, right? Based on which, actually the resistor feedback network, you can think of this guy along with this dimensional, play that we have here, A and B, right? So does it make sense now? Any questions up to this point? So we studied this separately, we studied this separately, and then we built a equivalent pneumatic system, and what do we call it? Is force distance. Why distance? Because of course force is there involved in the whole thing. Only thing that the input type is we are changing the distance here. Now there is one more kind of controller, a proportional controller, given by by the name of force balance. So here, if you see, right, there is as such no movement of the input signal is not given in terms of there is no flapper here wherein you are changing you are displacing the flapper position. So the advantage of this is it eliminates many mechanical linkages and pivot joints. In the previous diagram, we saw that there are two pivot joints, right? Here there are none actually, and thereby it reduces wear and tear by reducing the effects of friction, right? And the problem with this is, not problem, this is kind of understandable. This operates only on pressure signals, right? So the advantage of the earlier one is the input signal was in terms of displacement, right? And sometimes that is an easy thing to do, right? I mean, when we are actually trying to control something, it is for us, it might be very easy to, okay, we'll just give a displacement input signal, and then look at the final output pressure, right? So this operates only on pressure signal, unlike the force distance type. And so the error in the pressure that we are making, so this is atmospheric pressure. So let's look at the structure. We have a reference input pressure here, and this is the output pressure, right? And this is our air supply, which is equivalent to our power supply. Air supply and power supply, you can treat in electrical terms, you can treat it interchangeably. This is like our reference voltage. Reference input pressure is like our reference voltage. And this is our output pressure. So, and the error, so this output pressure can be thought of, if this was in feedback, right? We can think of this output pressure as a function of this control pressure. So this is what we want to control. But output pressure is like, you can think, so there will be some other linkage which will link the control pressure to the output pressure. So the error signal is given by the reference input pressure minus the output pressure. This we can understand, right? So this, so there is, so this structure based on the force difference, right, will change the gap here. So the average gap is, let's say, x bar, and the incremental small signal is x, and that will change incrementally, change the control pressure from average PC to an incremental amount small pc, right? Equilibrium, of course, as we know, that the error signal should be 0, right? The reference input pressure and the output pressure should be equal, right? Which means, okay, another thing that we have to see here is we have an orifice here, right? So whatever is the pressure that we get here, the control pressure, a portion of it goes here through this orifice, a portion of it. So essentially what happens, some portion of the air will flow out and it will develop. So whatever is the pressure here, a portion of it goes here, right? Similar, this of course you can treat as again a feedback that goes from here to here. And in that case, what we can say is x bar, we are talking in the equilibrium condition, is equal to alpha times the pressure that we see here. So this pressure, right, is A1. So if you see, this is PC. So the pressure that is applied on this surface is PC times A1, right? And what is the opposing pressure that we have is minus. So this pressure that we see here is PC times K times A1. Look at this carefully. Why we are saying this is at equilibrium? Because at that point, the pressure in this chamber and this chamber is equal. So there is no movement of this structure that happens because of a pressure difference between this guy, between this chamber and this chamber, right? At equilibrium, the reference pressure and the output pressure is 0. The difference is 0, right? So then whatever is the display, whatever is the location of this surface here, that will be given by the pressure difference seen at this chamber, and this is of course PC, right? Now, what happens when we move, because of, let's say we want to, create a actual difference, and let's say we move this point here by a small signal x. So then what happens, and how will we move this? By creating a change, creating a difference in this two, right? Let's say we'll change the reference pressure a little bit, right? If we change the reference pressure, what will happen? This guy will move, right? And what will be the movement? X bar plus x will be equal to the same constant alpha, and this constant alpha will be determined by how much this whole structure moves, right? This constant times alpha. So these two terms are understandable, right? because this is PC plus, like the capital PC plus small PC. This is the pressure here, multiplied by, of course, the area minus the pressure at this chamber multiplied by this area A1. Note that this area and this area is same, made same, minus, look at this term, and this is coming because of the error signal. This A2 minus A1, right? So this is the pressure that we are applying on A2 minus A1, right? That will be multiplied by the error signal here. So if you do a force balance equation at this point, you end up with this. And if I put this equation here, I can find out what is my incremental movement x as a function of the error signal and the control signal. So as x tends to 0, because at equilibrium x will tend to 0, right? At equilibrium there will be no more movement, right? Or x will be very small. At equilibrium x is tending to 0. For very small movement of x, right? We can say we can bring this guy here, do the math, and then we end up looking at the control signal PC as a function of the error signal PE, and this again is a proportionality constant, right? Right? So this is the proportional controller of force balance type. Here the input signal, please note, unlike in the force distance type, wherein it was easy to just give the input signal by moving the flapper, here the input signal is given by creating a pressure difference between the reference pressure and the output pressure. Okay. So K depends on the diameters of the, so this is understandable, right? Physically you should be able to understand based on what these, right now we are leaving most of these things to algebra. A detailed in-depth analysis, if we are going to do a structural analysis and all that, then we will be able to derive, these proportionality constants, right? But this is to kind of give you a flavor of the subject. So now let's look at pneumatic controllers and PD type. So which means proportional and differential, right? So here, if you see, we have, so this is, I think, a typo. This is, I think, a typo. No, 1 second. So no, this we actually had discussed, right? In the proportional controller for the displacement type, this we had discussed, right? So this was our displacement type, force distance type controller that we had discussed in the previous slide, right? So this is a proportional controller. Now, a proportional derivative controller, what we have done is we have introduced a resistor R here, and then what that does is, so this change, so what is the difference between this guy and this guy? From a proportional controller to a PD controller, the change that we have done is introduced a time delay, and this also we are now treating it as a capacitor. See, this is like, think of it electrically, right? We connect a voltage source directly across a capacitor, which means the capacitor will have no meaning, right? I mean, and that's the reason we never talk of a voltage source directly connected to a, we never talk of a capacitor directly connected to a voltage source, right? Meaning this capacitor becomes redundant, right? Because it doesn't matter. Whatever is the voltage will appear across these two terminals, right? However, if I introduce a delay, and that is what we do here by introducing an orifice or a valve here, right, which provides a resistance R, then we are bringing this guy into picture. A times Ks is still there because this is the force balance equation, right? So in the proportional controller, which we studied in the previous slide, just by making a small change of introducing a resistor here, and maybe you can say that, in this thing we didn't talk of the capacitance provided by the bellow, we just talked of the spring constant provided by the below, and we looked at the force equation and derived the rest of it, right? Here, this capacitance comes into picture, and then we end up getting a PD controller. And what does that mean? That if this is my error signal, right, X will look like this. You are differentiating this, right? This is a step that you are giving. A differential of that will give us something like this. And the control signal also will be having this kind of a settling behavior, right? So the the control signal as a function of the error signal can be written as this. I'm not driving, this is pretty straightforward to understand, but I think for you, right, for in this subject, right, what is important to understand is, other than understanding the, the effect of feedback and, the effect of, or rather how we are getting rid of the nonlinearity, right? What is important to understand is the electrical equivalent of these pneumatic controllers, right? How we can create an electrical equivalent, and then based on that, how we create, these transfer functions. I mean, we have to, of course, derive the block diagram, and based on that, we derive the transfer function, right? So based on that, we can realize different kinds of controllers. And of course, we can make the loop gain 0. And if we make the loop gain 0, loop gain as high as possible, so that this guy becomes much higher compared to 1, and then this denominator will cancel out. B by A, of course, will stay. K cancels out, and this guy comes on top, and then we realize this kind of a transfer function. So this we have this we have discussed in the electrical context also, that why we want to make the loop gain as high as possible, right? So this gives the PD controller, and similarly a PI controller. Quickly, we don't have much time left, but let's look at the PI controllers. So PI controllers we have. So what do we do for PI? Or maybe we'll stop here and look at the PI controller tomorrow, because otherwise we'll not be able to do justice to this. So we'll stop now today, and we'll continue tomorrow.